All right, let's talk about 1.6. Ooh, let me focus. There we go. 1.6 about the continuity of trigonometric functions. So basically, the trigonometric functions are continuous on their domains. And this is not something that we're going to prove, but it should be fairly intuitive, right? That the trigonometric functions are going to be continuous. Now, we need to be careful with this, though, right? The fact that the trigonometric functions are continuous on the domains, that doesn't mean that they're continuous on all real numbers, right? They're not necessarily continuous on the set of all real numbers. Sine and cosine are continuous on the reals because the domains of sine and cosine are all real numbers. But tangent, cotangent, secant, and cosecant, now those functions do not have domain all real numbers. Right, the tangent function has asymptotes at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and then every odd integer multiple of pi over 2 after that, right? So it has a bunch of discontinuities if you're looking at the entire set of real numbers. But the thing is that pi over 2, negative pi over 2, etc., these things are not in the domain of the tangent function. So it still remains true that tangent is continuous on its domain. Right? On its domain, it's a continuous function. Same thing with cotangent, secant, and cosecant, right? They all of those functions have asymptotes at various places, but on their domains, they are continuous functions. But notice that since the trig functions are continuous on their domains, that means that the limit as x approaches c of whatever trig function of x equals that trig function of c. So in particular, right, limit as x approaches c of sine x equals sine of c, and limit as x approaches c of cosecant x equals cosecant c for every real number c in the domain of that trig function. And that's the key, right? It has to be in the actual domain of the trig function. Obviously, limit as x approaches pi over 2 of tangent x, right? That's not equal to tangent of pi over 2 because tangent of pi over 2 is undefined, right? So really, if you actually look at the graph of the tangent function, you would see that that limit is it doesn't exist. You approach positive infinity from the from which direction? From the right you approach from the left you approach positive infinity, and from the right you approach negative infinity. If you're looking at the graph of the tangent function. But anyway, as long as c is in the domain of the trig function, then this limit exists, and it's just equal to that trig function value. So let me give you a couple examples of this. So let's find the limit. Part A, let's do limit as x approaches 3 of tangent of x minus 3 over x squared minus 2x minus 3. Okay. Now, if you try direct substitution here, you're going to get tangent of 0 over 0. I think, right? 9 minus 6 minus 3, yeah, 0. So you get so if you try direct substitution, you would get 0 over 0. Right? And so what that tells you is that you've got to do a little bit more work. You can probably do some kind of algebraic manipulation to cancel off like a common factor in here. So in particular, we can factor this this denominator and then hopefully cancel the x minus 3 in both locations. If there is a factor of x minus 3 in the denominator, hopefully there is. What makes this work, though, is the fact that since tangent is continuous, limit as x approaches 3 of tangent of some thing, g of x, right, is the same thing as tangent of the limit as x approaches 3 of g. In other words, we can take this limit and we can put it inside of this argument here because tangent is a continuous function. So we can say, well, this is equal to tangent of the limit as x approaches 3 of x minus 3 over x squared minus 2x minus 3. And you don't always have to show this step. I'm just showing you why the fact that the trigonometric functions are continuous, why that's important. Because if they weren't continuous, then you wouldn't be able to do this, right? But because they're continuous, you can move the limit inside of here. Because tangent is continuous, you can move the limit inside of there. And then really this just boils down to trying to find this limit. So this is going to be tangent of limit as x approaches 3 of x minus 3 over, and then this thing factors as x minus 3 and x plus 1, which is really convenient for us, right? Because then the x minus 3's cancel. We get tangent of limit as x approaches 3 of 1 over x plus 1. So we plug in 3 now, and we're just going to get 1/4. So this is equal to tangent of 1/4, whatever that is, right? By the way, unless there's explicitly a degree on the number, we're assuming that we're working with radians. So this is not tangent of 1/4 degrees. This is tangent of 1/4 radians. So make sure that your calculator is in radian mode when you're doing this section. So you could plug in tangent of 1/4 into your calculator to see about how much that is. I'm not really interested in that, at least not for now. So that's that one. Let me give you another example. Let's look at limit as x approaches positive infinity of sine of pi x over 2 minus 3x. So again, because sine is continuous, we can just move this limit inside of here. We can say, well, this is the same thing as sine of limit as x approaches positive infinity of pi x over 2 minus 3x. Now, if you imagine plugging in bigger and bigger numbers for x, what's going to happen is that you're going to get a really huge number in the numerator and a really huge number in the denominator, right? You're going to get infinity over infinity, essentially. But notice that these are really polynomials. It's kind of weird because we have pi as a coefficient in the numerator, but pi is just a number, right? It's just like saying 7x over 2 minus 3x or something like that. Only instead of 7, of course, it's pi, about 3.14. Well, so what we learned about limits as x approaches infinity of rational functions is that the limits are equal to the ratio of the leading coefficients. Or maybe a better way to say it is that they only the leading term really matters. All of the other terms are negligible. So, and by the way, this is only true for limits as x goes to positive or negative infinity. It's not true for limits as x approaches some finite value. But for limits as x approaches infinity, this is exactly the same thing as just looking at limit as x approaches positive infinity of pi x over negative 3x, right? That 2 really isn't going to contribute much. Once x gets really, really big, this 2 is not going to matter, right? It's not going to change the value by much. And the benefit to this is that we can now cancel the x's. We get sine of limit as x approaches positive infinity of negative pi over 3. Notice that this expression doesn't have any x's in it. So as x approaches infinity, negative pi over 3 is going to be negative pi over 3, right? So this is just sine of negative pi over 3. And that value we can figure out. Sine of positive pi over 3 is root 3 over 2. So sine of negative pi over 3 is negative root 3 over 2. Sine is an odd function, right? So sine of negative x equals negative sine of x, right? Anyway, so negative root 3 over 2. That's the other thing about these trig things in calculus class, where we work with radians most of the time, and we prefer exact answers when we can get them. So if you're using your calculator, and what would this be if you used your calculator? So if you have a nice calculator like mine, it'll give you the exact value. in which case, you know, you're welcome to use, oh, I'm in the wrong mode. I've got to change to radian mode. Here we go. Okay, so if you've got a nice calculator like mine, then, you know, it'll give you the exact value, negative root 3 over 2. But if you don't, then it'll give you some kind of irrational decimal number like this, and do not give this answer to me. I'll take a point off at least on a test or a quiz. I want to see the exact answers whenever it's possible to get them. So that means that, you know, you should take some time memorizing the unit circle. Maybe I'll post a unit circle with these notes. In fact, I think I will when I post this video. So I'll post a unit circle so that you can memorize these trig function values, kind of the standard trig function values. So you should know sine and cosine of 0, pi over 6, pi over 4, pi over 3, pi over 2. You should just have those memorized. Anyway, so now the next thing I want to do is let's consider the limit as x approaches 0 of sine x over x. So if we try direct substitution here, you know, if we just plug in 0 for x, we're going to get sine of 0 is 0. And, you know, when we plug in 0 for x, we get 0. So we get 0 over 0. Anytime you end up with 0 over 0, as opposed to, say, you know, 7 over 0 or something like that, anytime you end up with 0 over 0, that tells you that usually the limit exists, and we can do some kind of manipulation to try to find it. However, in this particular case, there's not an easy algebraic manipulation that we can perform to figure out what limit as x approaches 0 of sine x over x is. One thing that we could do is we could look at a graph of it to kind of develop our intuition a little bit. So let me pull up Desmos. Okay, so we could look at sine x over x. And it seems like as x approaches 0, we're probably approaching 1, even though the function is undefined there. But it seems like that's the value we're probably approaching is 1. But how to show this kind of algebraically, I guess? Like what's a proof of this fact? Well, the proof of this fact is going to rely on something called the squeeze theorem, or your book calls it the squeezing theorem. But I've always heard it referred to as the squeeze theorem. Anyway, the squeezing theorem says this. It says, so let's say that f, g, and h are all functions such that f of x is always bigger than g of x, but always smaller than h of x, right? So f of x is somewhere between g of x and h of x inside of some open interval containing c, right? With the possible exception that the inequalities need not hold at c itself, which is a minor detail. Okay, but now let's say that these outside functions, right, g of x and h of x, have the same limit as x approaches c, right? So limit as x approaches c of g of x is the same as limit as x approaches c of h of x, and let's say that limit is L, right? So if f of x is trapped between g and h both go to the same limit, then f of x must also go to the same limit. And I've got a typo here. Let me fix that. It should say f of x, not h of x, right? So then f of x also goes to L, right? Which almost sounds like I'm cursing. But no, it's right. That should make some sense to you. If f is always trapped between g and h and h are both going to the same limit, well then f has no choice but to go to that limit as well, right? Here's a picture. So I've got f in red, h in blue, and g in green, right? And sometimes, so over here, f is bigger than h actually, but inside of some interval containing c. So we'll say like inside of this interval, notice that f is always larger than g but smaller than h, right? So f is always between g and h. And notice that g and h are both going to L as x approaches c. If that's the case, and if f is always trapped between those two functions within this interval, well then f must also go to c, or sorry, f must also go to L as x approaches c, right? It's got to be kind of pinched or squeezed inside of there. And so that's what the squeeze theorem says. I don't know if I'm going to go through this in detail, but here's a proof of the squeeze theorem that you're kind of welcome to kind of pause the video and read through yourself. But basically the idea is that, you know, if we know that limit as x approaches c of g of x equals L, then that means that for every epsilon bigger than 0, we can always find a delta, and I'm calling this delta 1, so that, you know, this condition is met, right? And similarly for h of x, right? It means that for every epsilon bigger than 0, there's a different delta, right? So we'll call it delta 2, but there's a different delta so that this is going to be less than epsilon. And if that's the case, well, so then let's say that epsilon is bigger than 0, and let's choose delta to be whichever of those two deltas is smaller, okay? And then if that's the case, we can guarantee both of these conditions, right? And moreover, since f is always between g and h, we can guarantee this third condition. So if you piece these three conditions together, what you get is this long inequality, right? You see that negative epsilon is less than g of x minus L, which is less than f of x minus L, which is less than h of x minus L, which is less than epsilon. So if you drop the middlemen, what you really have is f of x minus L is somewhere between negative epsilon and positive epsilon, or in other words, f of x minus L is less than epsilon. Okay, so that's the proof of the squeeze theorem. Again, I'm kind of running through the details pretty quickly, but that's the idea there. So right off the bat, so let me say this, right? You're probably, I squeezed this comment in here after I wrote out my notes, after I looked at your homework problems, because it turns out that you don't really use the squeeze theorem that often in your homework problems. What you are going to use are these facts in this next theorem, but in order to establish these facts, we need the squeeze theorem. Okay. So so you probably, I think you do have maybe one or two problems where you have to use the squeeze theorem, but for the most part, you're just gonna be using these facts here, some version of these facts. So that limit that we were talking about earlier, right? Limit as x approaches 0 of sine x over x, and we looked at the graph of it, and we thought that it kind of looks like it goes to 1, and that does in fact. That is in fact true, right? So limit as x approaches 0 of sine x over x equals 1. And then similarly, if you flip this over and you look at limit as x approaches 0 of x over sine x, that also equals 1. And then finally, we have a kind of a similar statement for cosine, right? So if you think about limit as x approaches 0 of 1 minus cosine x over x, if you try direct substitution on that, cosine of 0 is 1. So you would have 1 minus 1, which is 0. So you get a 0 over 0 thing again. But again, there's not an easy algebraic manipulation to sort of take care of that. So so here's what we do, right? So I'm gonna show you the proof of the fact that limit as x approaches 0 of sine x over x equals 1, and it's just going to be a kind of a sketch of the proof. So the sketch works like this. First of all, you can establish the fact that sine x over x is always between cosine x and 1, right? So that can be shown, and this proof is in the book. So the proof of the squeeze theorem was not in the book, but this proof is in the book. And so if you're interested in the details for how we end up with this inequality right here, then take a look at the book. But this is the first thing that you would do. You would establish the fact that sine x over x is always between cosine x and 1. And now what we do is we apply the squeeze theorem, right? Because limit as x approaches 0 of cosine x is just the same thing as cosine of 0, because cosine is a continuous function. Right? So this is just cosine of 0. Cosine of 0 is 1. So limit as x approaches 0 cosine x equals 1. Meanwhile, if you look at limit as x approaches 0 of 1, that's also going to be 1, because that function is not dependent on x at all. It's just a constant function. So as x goes to 0, 1 goes to 1, of course. Right? So the limit as x approaches 0 of cosine x equals the limit as x approaches 0 of 1. Right? They're both equal to 1. And since sine x over x is always between cosine x and 1, and since these things are both going to 1 as x goes to 0, that means this thing must also go to 1 as x goes to 0, right? So that's by the squeezing theorem. Okay? So really the big trick on this proof is, well, first of all, applying the squeeze theorem, but the main thing is showing this inequality, which again, the details for that are in the book. Okay, but the squeeze theorem allows us to conclude that this limit is in fact 1. Okay. And then to show this second limit, right, limit as x approaches 0 of 1 minus cosine x over x equals 0, right, to show that, we actually don't use the squeeze theorem for that at all, but what we do use is part A of the proof, right? So we start with this limit, and then we multiply by the conjugate, 1 plus cosine x over 1 plus cosine x. What you end up with then is 1 minus cosine squared x, right? When you FOIL out the numerator, you end up with 1 minus cosine squared x. And you may recognize a Pythagorean identity there, right? 1 minus cosine x is the same thing as sine squared x. So maybe I'll also post a list of identities for you to kind of print out and have on hand with these notes. But 1 minus cosine squared x turns out is the same thing as sine squared x, right? Now, the trick is, we know that limit as x approaches 0 of sine x over x equals 1. So if we can pull out a sine x over x, then we know that that limit's going to be 1, and then we'll deal with whatever we have left over after that. And so we're going to do that, right? We're going to take out one of these sine x's, and we're going to take this x out, and what we would be left with is another sine x in the numerator, and then the 1 plus cosine x in the denominator, right? And we can distribute the limit to each of those. Remember that limits distribute across multiplication, so we can go ahead and distribute the limit this way. Now, limit as x approaches 0 sine x over x equals 1. We just proved that in part A. Limit as x approaches 0 of sine x over 1 plus cosine x is, well, we can just use direct substitution. We can plug in 0. Sine of 0 is 0. So we get 0 in the numerator, and then in the denominator we're going to have 1 plus cosine of 0. Cosine of 0 is 1. Right, well, 0 over 1 plus 1 is just 0 over 2. 0 over 2 is just 0. And 1 times 0 is 0. Right? So we've proven part B as well. So, these two facts, right, are very useful for us. They'll be useful for you in the homework as well. And I'll show you how. So let's look at a few more examples. Okay, so we're looking for limit as x approaches 0 of sine 4x over x. What we know is that limit as x approaches 0 of sine x over x equals 1, right? So, well, we'll just say limit as x approaches 0 of sine x over x equals 1. So this is a key fact here. Now, here we have limit as x approaches 0 of sine 4x over x. What we need is for these things right here to match. Okay, so we need the argument of our sine function to match the denominator down here. If we have that, then we can conclude that sine of whatever over that same thing, the limit as x approaches 0 of that is going to be 1. So what we need to do in this case is multiply by 4 over 4. Right? And then what I'm going to do is I'm going to take this 4 out. So I'm going to call this 4 times limit as x approaches 0 of sine 4x over 4x. And now this limit is 1. So we get 4 times 1, which equals 4. Okay? So that limit should be 4. And that's sort of the key on these kinds of problems, is that you're going to try to manipulate whatever you're given to be in the form sine x over x, either in the form sine x over x, or you might want to get it in the form 1 minus cosine x over x. Or maybe you get it in the form x over sine x, right? But you want to get it into one of those 3 forms that we just proved on the previous, or that we just finished proving, right? So let me give you another example of this. So let's do limit as x approaches 0 of tangent x over x. If you try, so you should always try direct substitution first, right? Just to see. If we try direct substitution, though, we're going to get tangent of 0, which is 0, over 0. So we're going to get a 0 over 0, right? So we have to do some kind of algebraic manipulation. Now, one thing that you can do is change. You can always change tangent into sines and cosines, right? So tangent is just sine over cosine. So I'm going to call this sine x over x times cosine x, right? Because the sine over cosine is just the equivalent to the tangent, right? Well, so now you probably notice that you've got a sine x over x, right? So we can call this limit as x approaches 0 of sine x over x times 1 over cosine x. Okay, now I'm not going to show the next step of like distributing the limit to each of these things, but we know that we can do that, and I'm just going to kind of do that in my head. So limit as x approaches 0 of sine x over x is 1. So I know that this thing goes to 1. Limit as x approaches 0 of 1 over cosine x, well, that would be 1 over cosine of 0. Cosine of 0 is 1. So this would just be 1 over 1, which is also 1. So this is just 1 times 1, right, which equals 1. Okay, so that's kind of nice to know. Okay, so let's do another one. Let's do limit as x approaches 0 of sine 3x over sine 5x. Okay, I'm going to have to pause real quick. I'll be right back. Okay, sorry about that. Okay, so limit as x approaches 0 of sine 3x over sine 5x. What do we do about this thing? So our goal should be to make it look like sine x over x, where this x and this x match, of course. So I think I can force it by if I multiply by 1 over x in the numerator and denominator, then I get limit as x approaches 0 of sine 3x over x over sine 5x over x. Okay, so that's still not quite right, because I need for the denominator to match the argument. So like in this case, I can multiply by 3 over 3, and in this case, I can multiply by 5 over 5, right? So I'm just multiplying by ones, essentially, which means that I'm not changing the value of anything here. So this gives us limit as x approaches 0. This 3 and this 5, I'm going to take out. They're going to end up as a 3/5 out here. So maybe I'll call this 3/5 times the limit as x approaches 0 of sine 3x over 3x over sine 5x over 5x. Now I'm not going to show the next step, but we know that we can distribute limits across quotients. So I can take the limit and just look at the limit of sine 3x over 3x. Well, I know that that's 1. And I can do limit as x approaches 0 sine 5x over 5x. That's also 1. Okay, so this is 3/5 times 1 over 1, which is of course just 3/5. And that's that limit. Okay, so the moral of the story is you try to rewrite stuff in terms of, you try to rewrite it so that it looks like sine x over x, or, x over sine x, or 1 minus cosine x over x, right? Any of those things. Okay. But I did want to give you an example of some squeeze theorem stuff, just so that if you do, because I think you will encounter maybe a problem or two that require you to use the squeeze theorem to find the limit. So let's find the limit. Find the limit if it exists. So first, let's consider limit as x approaches 0 of sine of 1 over x. So first of all, we know that sine x is always between -1 and +1. So that means that sine of 1 over x also has to be between -1 and +1, right? Like the output values of the sine function are always going to be between -1 and +1. Now the question is, what's happening as x gets closer and closer to 0? So as we plug in smaller and smaller values for x, this fraction gets larger and larger. And in fact, the smaller we get, the larger the function value gets. So that the closer we get to 0, the more the sine function is going to sort of fluctuate between -1 and +1, right? Like it's going to start to oscillate more and more rapidly the closer and closer that we get to 0. So I'm kind of thinking of a picture that sort of looks like this. Because notice that on the other hand, as x gets really large, right, as x goes to infinity, this fraction gets really small. So as x goes to infinity, same thing as x goes to -infinity, this fraction gets really small. And so it gets really, really close to 0. And sine of 0 is 0. So out here, I think we're approaching closer and closer and closer to 0, like out in the tails. Over here on the left, I think it would look maybe more, a little bit more like this, but still approaching 0 from the other side. And then maybe this is 1 and -1 or whatever. And then it must do something kind of like this, where it starts to oscillate really quickly, right, from either direction. Right? That's a horrible, ugly picture. But I think that's kind of the idea. So if we're asking what's the limit as x approaches 0 of sine 1 over x, well shoot, is it 1? Is it -1? Is it 0? My feeling is that this limit does not exist, right? So I'm going to say the limit does not exist. It doesn't seem like we're approaching any given value, right? We're not approaching any given value. We can verify this by taking a look at Desmos. So let's take a look at this thing in Desmos. Whoops, sine 1 over x. Okay, so there we go. Oh, this is a much prettier picture. But it's doing kind of like what I said, right? Approaching 0 as you go to negative infinity, approaching 0 as you go to positive infinity. But as you get closer and closer to 0, as x gets closer and closer to 0, this thing just starts to oscillate really quickly. And you can zoom in and you can see that, yeah, this thing is just alternating between -1 and +1, but more and more densely the closer you get to 0. So it's really kind of a crazy thing. Really cool, I think, but kind of crazy. So it's impossible to say that the limit exists. In fact, we can say definitively that the limit does not exist. It would be a fun exercise to prove that. So it would be an interesting exercise to prove that the limit as x approaches 0 of sine of 1 over x does not exist. What that would entail, and when I say prove it, I mean using the epsilon delta definition, right? So because if the limit exists, and let's say the limit is L, then the definition says that for every epsilon bigger than 0, there's a delta such that x minus 0, or so in this case just absolute value of x, less than delta implies that absolute value of sine of 1 over x minus L is less than epsilon. So that would be if the limit exists. So if the limit doesn't exist, what would that mean? Well, that would mean that there exists some epsilon such that no matter what delta you choose, the function value is never going to be within epsilon of that value. So in particular, I'd have to give it some thought, but I think in particular you could choose epsilon to be 1, right? Yeah. So there are some details that we'd have to crank out, but it's like obviously, this thing is going to fluctuate between -1 and +1. So maybe to be on the safe side, you could even choose epsilon to be like half, like 1/2, because I guess I'm kind of assuming that the limit's 0 in that case. But anyway, so there are some details, but I think it would be a good exercise to prove that this limit doesn't actually exist. But here's what I really wanted to do, though. What I wanted to do is contrast that with this function. So let's look at limit as x approaches 0 of x times sine of 1 over x. Okay. Now, what's going to go on here? You'll notice that since sine of 1 over x fluctuates between -1 and +1, but as x goes to 0, x is going to get closer and closer to 0. So in some sense, that's going to sort of like tame the graph a little bit. So I'm kind of thinking that you end up with a situation that must look kind of something like this, right? So this is x, and sine of x is going to fluctuate between -1 and +1. But I think you've got to end up with something that sort of looks like this. Right? Like it seems like that's kind of what's going to be happening here. And if that's the case, then it seems like the limit should be 0. And in fact, that's exactly what the squeeze theorem says, right? So here's what I'm going to say. So I'm going to say, note, I'll say since sine of 1 over x is between -1 and +1, it should be the case that -1 times x is less than or equal to x times sine of 1 over x, which is less than or equal to 1 times x, right? Right? So sine x is between -1 and +1. That means x times sine of 1 over x is between x times -1 and x times +1. So in other words, we have -x is less than or equal to sine x times sine of 1 over x, which is less than or equal to +x. Okay, so notice that limit as x goes to 0 of negative x equals 0, and limit as x approaches 0 of x also equals 0, right? Both of those things go to 0. So since x times sine of 1 over x is trapped between negative x and positive x, and since these things both go to 0 as x goes to 0, x times sine of 1 over x must also go to 0, right? Therefore, and this is by the squeeze theorem, right? So by the squeeze theorem, limit as x approaches 0 of x times sine of 1 over x equals 0. Let's take a look at this in Desmos. So the blue stuff is sine of 1 over x. Let's look at x times sine of 1 over x. Okay, so it's in green. So you'll notice that, yeah, well, let's kind of hide the blue one for a second. So that's interesting, what's going on there. And in fact, I'm going to graph x and negative x. Let's make them the same color. Maybe make them dotted or something. Okay, but anyway, yeah, so you can see that the green function, x times sine of 1 over x, is trapped. It's trapped between positive x and negative x. Kind of nice, really pretty cool, I think. But yeah, the limit's going to 0 for sure. So notice that the same thing happens, like it's oscillating more and more densely the closer and closer that you get to 0, but the function values are sort of tamed by the fact that you're multiplying by x, right? So they're oscillating, but they're still getting closer and closer to 0, right? Closer and closer to 0. Anyway, cool stuff, I think. But that's that. So if you come across a problem that requires you to use the squeeze theorem, then this is the idea. The idea is that you want to try to trap this function between two functions that have the same limit, okay? And that's the key. It's pretty easy to trap a function between two different functions most of the time, but the key is that you have to trap them between two functions that have the same limit. That's the key, and that's a little tricky. But with trig functions, well, with sine and cosine anyway, you can always trap them between -1 and +1, and that usually does the trick. But anyway, so that's that. That's all I'll say about that stuff for now.